two PhD students, Rob and May, who were both master's students at the time. Is that better? Yeah. Myself and Carlo, who's in the audience. So the motivation comes from these two seminal papers, which many people will be familiar with. So on the left, a paper by Keith Moffat introducing the concept of kinetic helicity. On the right, Woodger, that's probably a terrible pronunciation, who introduced the concept of magnetic helicity. These ideas of a way to quantify the amount of twisting or braiding of either magnetic field lines, magnetic flux tubes, or vortices in a classical fluid. And the reason why these are important is they're both invariants in ideal fluids or ideal MHD. And I guess the cutting-edge experimental probing of these results are experiments performed in Chicago by a group of William Irvine, looking at the dissipation of helicity in water. I'll show a movie which is sort of obligatory when you're giving these talks on knots of moving aerofoil through water and visualizing with bubbles. And the group of Carrie Forrest in Wisconsin, where they have this plasma dynamo set up, where they're probing the role of magnetic helicity in constraining the generation of a large-scale dynamo. So this is the sort of cutting-edge experimental results. Probably today won't be the cutting-edge numerical results, but I'll show you, hopefully I'll motivate why quantum fluids are ideal candidates for looking at topology, and I'll show some of the results that we've published recently. Okay, and obviously we all know that BCs, or superfluid helium, are also not ideal fluids, but what I want to argue in this slide is that they're ideal playground for investigating ideas of topological fluid dynamics. And on the left, we see a sort of classic simulation. Oops. My wife broke this adapter, and it's a bit finicky. I blame my wife, obviously, it's probably me. Yep, so on the left we have a classic simulation of resistive MHD performed by Axel Brandenburg and his group a few years ago. So they initialized a trefoil knot in the magnetic field and let this evolve in time. So I think the time goes this way. And you see very quickly things get very messy. So what's plotted are magnetic field lines. So they're simply plotting dx by dt is the vector field B. And very quickly you see it gets messy. These magnetic field lines reach the edge of the box, and so defining topological quantities would be quite difficult. If you were interested in, say, topological properties of the underlying field, so you wanted to look at something like isosurfaces of the magnitude of B, it's not entirely clear that your topological quantity would be invariant under the isosurface level that you took. Has anyone got a better adapter? Can I pinch yours? Yeah, it's a USB-C to HDMI. Sorry. So on the right, if you remember, there are isosurfaces of low density in a GPE simulation from the group of Dan Lathrop in Maryland. This McKee is just a journalist who wrote this article for PNAS. This is a zoom in of a large simulation where you see this tangled complex field, these knotted quantized vortices, and obviously the topological properties of this, as long as you're sensible with the isosurface that you take, should be invariant under this isosurface. So as long as you're picking out the core of these quantized vortices, you'd expect things like linking or writhe or knotted properties of this tangle would be invariant. Okay, and that's, I think, one of the prime reasons why quantized fluids, or quantum fluids, are prime for investigating topological fluid dynamics. Okay, so the sort of schematic of what I want to do is take the notion of classical vorticity, pass it through even the sort of paradigm of a quantum fluid, so here depicted by Camerlinger-Oddens and the Blue Boys of Leiden, who were first to realize the liquefaction of helium and superfluidity, and realize quantized vortices, which we see here from, again, the group of Dan Lathrop in Maryland, where you see these quantized vortex lines dressed with helium or deuterium particles. Okay, and so it'll be this side of things, focus more on helium, but everything that I say is applicable to BECs as well. So knots, the idea of the motivation of this talk was looking at knots, or the idea of a knot spectrum and knot distribution in quantum turbulence. And of course, knots are this archetypical example of low-dimensional topology. So one of the prime examples, if you're a low-dimensional topologist worth his salt, and any grant application that you make, of course, you'll appeal to DNA as this molecule, which is obviously important, but is also found to be knotted. There are other applications, so material science, here we see some polymer chain that's densely knotted, and if I remember, the application of this is some sort of improved bulletproof vest, and I'm sure there are less aggressive examples of where knots can be used. Knots are intimately related to braids as well, so if we take a braided structure and connect it back up, we form a knot. And braids are also observed in many physical systems. One of the prime examples are in solar flares, so in the convection zone of the sun, strong magnetic fields are generated, the magnetic pressure pushes out plasma, these flux tubes become buoyant, erupt through the surface, and then at the surface there are these turbulent foot point motions, which you can see visualized here. These tangle up these erupting flux tubes, and people use tools from braid theory to try to quantify the complexity and try to understand how these magnetic fields will subsequently relax, reconnect, release energy to heat the corona, and also perhaps interfere with satellites. And a more left field example, something else that I'm interested in, is collective motion in animal systems. So this is a numerical simulation of a well-cited model of collective motion in three-dimensional systems like birds, and these particles obey some rule which tells you how they align with other particles, and if you connect up their trajectories, the numerical model makes predictions, well, the underlying analytic model makes predictions about the braiding of these trajectories, and then if you can visualize three-dimensional trajectories of birds using techniques from particle tracking in turbulence, which a group in Rome have done with starlings, maybe you can start to test models of collective motion by using tools from braid theory. Okay, so that's a motivation to look at knots. Of course, it would be a crime not to show this movie. I'm sure it won't be the only time we see it this week. I'm sure we saw it last week at the workshop. So vortex knots have been talked about in fluids, but were realized really a few years ago by the group of William Irvine, who dragged these aerofoils that were 3D printed through a fluid very quickly, you'll see in the movie, and generate either perturbed loops or vortex knots. So here we see just a perturbed loop which propagates up and is essentially visualized with bubbles in the fluid. So this is a classic experiment. And here we see a knot, the trefoil. And they've got this nice matrix-style kind of visualization. I think is it to view it in 3 dimensions if you've got specs? I wasn't prepared enough to bring specs for everyone, but I think if you've got, red and green spectacles, you can view it in 3 dimensions, like you're watching sort of Attack of the Dinosaurs at the movie, at the cinema. The key thing I want to stress here is that this is a link which I won't really touch much on in this talk, is that this knot is metastable. In fact, it's very unstable and falls apart very quickly due to viscous effects and reconnections. And maybe there was a hint going back into the past, and these papers weren't really motivated by quantum fluids per se, but the local induction approximation. I've not put the formula up, but if you're not familiar with it, we can think of it as the simplest, quite naive model for the motion of a quantized vortex. So it comes from the Biot-Savart and essentially expanding and keeping the leading order term. And papers by Kida and then Rika maybe hinted that in a quantum fluid, a vortex knot was a much more stable object. So there's a certain class of knots, I'll show you one on the next slide, called a torus knot, and Rika proved that if the deformation of the torus knot wasn't too large, then for these particular types of torus knots, where one of the winding is larger than the other one, then these were stable under the local induction approximation. And we can visualize this by solving the local induction approximation for one of these knots, the torus knot 2-3. And the box here is just for visualization. This is purely a simulation performed in free space, in an infinite volume. And this guy wobbles a bit as it moves, but essentially propagates up and see if we can watch it again. And is a stable topological object. Of course, in reality, things are probably not quite so simple. Finding these restricted torus knots is probably not what you see. And later work by Davide and Carlo, and I apologize for the music, this is not me, this is on them. Oops. So I don't know who's the jazz fan. Davide? Yeah. I'll skip ahead just in terms of time. So they describe what they're doing, but they're essentially looking at the same sort of thing, although the perturbation on the knots is a little bit larger. But these are torus knots, but now in the Gross-Patievsky model. The boundaries of this box are solid, so if you see it reconnecting with the boundaries, it's just reconnecting with its image. And these look more like the knots of William Irvine. But they're very unstable. They propagate up, but very quickly reconnect. Okay, and so the question motivated by these two extremes is, if we look at a tangle of quantized vortices in a typical experiment, say, do we find knots, or are these things too fragile? So this is a schematic of an experiment performed at Lancaster, where one of the wires moves back and forwards, sort of not quite analogous, but just think of me wafting backwards and forwards and generating a localized cloud of turbulence above my head. So in a similar way, this wire flapping backwards and forwards creates a localized tangle of quantized vortices. So these are experiments performed in superfluid helium-3, but for the purposes of what we're interested in today, it doesn't really matter. It's just a cloud of quantized vortices. And the question is, if we look into this tangle, do we find a book of saline knots? Or do we find these knots, or based on simulations with the GPE and other simulations with the BSFR, are these things simply just too fragile to actually find? Okay, so let's sort of tighten up what we mean by a knot. So I'm simply talking about a closed curve in three-dimensional space, which would obviously fit with a simulation of quantum turbulence in 3 dimensions. And typically we would view them as a projection in R2. That's fine, we can apply centuries worth of mathematics that's been developed in this area. So there's a very formal way. What we're interested in, I guess, is trying to identify if a very complicated tangled quantized vortex is really something much simpler. Okay, and so what we want to relate is this thing really just a very simple knot, or actually not even a knot at all, but just a closed loop that's been deformed by nonlinear interactions with other vortices. Okay, and so there's this more formal mathematical way of saying two knots are equivalent if we can perform this orientation-preserving homeomorphism. What that really means is just don't chop the rope. So here's some climber, and this is not really a knot at present, but just imagine that this thing connects back round and forms a closed loop. Okay, and then locally he performs this perturbation to the knot by twisting it around his hand, but he's not chopping it. Okay, and this is a sort of physical example of this more mathematical idea of this homeomorphism. And it was Kurt Reidemeister in the early 20s who really formalized this. So here he is with a sort of, if you zoom in, it's bizarre. He's got some sort of small jaguar that he's about to perform topology with. But he really formalized things with these 3 maneuvers, which are now called the Reidemeister moves. And essentially, if I can take any knot, apply these moves, and create a space curve which lies on top of another knot, then these 2 things are said to be equivalent. Okay, and so that's the way that we can relate 2 knots. So a tiny little bit of history. So I'm guessing everyone here, particularly with Kelvin waves, but Kelvin is obviously one of the pillar stones of modern science. I'm sure people are familiar with Lord Kelvin on the left. Perhaps not as well known as his contemporary Peter Tate. And I've just put their sort of births and deaths and where they were both chairs just to emphasize the huge overlap that these two men had. In fact, they published a very famous treatise on natural philosophy together, the sort of Tate and Thompson treatise. And it was really Tate, if you're familiar with Kelvin's ideas of elements being distinguished by different knots in the ether, it was really Tate that provoked this idea. And so here's a nice sketch of one of Peter Tate's experiments. I don't know where this was performed, but one of the first people to have a generator of vortex rings. So like you would buy if you were, I have it when I'm teaching undergraduates, you can buy these vortex ring generators where you smack a membrane and through a small orifice you create a vortex ring. So he was one of the first people to do this. You can see this membrane here and whoever it is about to smack it, and I have to imagine it's some sort of pipe tobacco or God knows what smoke inside this thing. But by creating these vortex rings, Kelvin was astonished by how stable as a topological object these vortex rings were, and proposed that elements, the atoms that formed the different elements, were just different knots in the ether. And this came towards the end of the 19th century with a couple of papers by Kelvin. And looking at Tate's sort of knot tables, you can see where this idea of squaring the circle with Mendeley's periodic table came, because there is this sort of natural classification of these different knots. So this table is simply loops with different crossings. And so you see the unknot, there's only one way, once you really simplify the unknot, of realizing it. The trefoil knot, a knot with 3 crossings, there's only one unique way to do this, it's the trefoil knot. But once we get to 5 or 6 crossings, it simply becomes combinatorics, and there are far more ways to realize a knot with a different number of crossings. Okay, and so if I went back, my sort of naive idea was, do we find this book of sailing knots? Well, actually, if you look at these guys, these aren't really mathematical knots. Their ends aren't connected. So actually, what perhaps we should be doing is repeating this, a bit giddy, but looking at this tangle, actually seeing, do we find this Tate table of knots, and can we count how many different knots fall within these different, within the different classifications? And could we do this? Could this be done with experimental data or numerical data? I think perhaps. I mean, it's not what we're going to do here, but I'll illustrate how it could be done. So we would look inside a 3-dimensional tangle if we had advanced 3-dimensional visualization, which is coming in experiments with superfluid helium at least. Then we could take this complex knot, pass it through some function which relaxes it. So this will be Wednesday afternoon for everyone. Took a while to find this photo. And find that actually this quite complicated knot is actually something much more simple that we can tie into Tate's tables of knots. And that could be done. So there's a package which is commonly used by people in low-dimensional topology, which does this relaxation for you. So here we see this complicated knot. I confess I don't know what algorithm is used in this, but some sort of minimization of energy, I guess. And this can be downloaded. It's not a free piece of software, but it's pretty cheap. Potentially. Now, I think the software can move quicker. This is snapshots to make the movie run smoothly. But in the end, you see that you can take this knot and then map it to Tate's tables to see if you can find what knots are in your tangle. Okay, now I agree this is pretty slow, so there are other techniques. There are various algorithms that have been proposed. This is just a recent one that I point out just because it's colleagues down the road in Durham where they proposed this reaction diffusion model to untie vortex knots. So it's not something that I'll do today, but it's something I just want to point out that it is a feasible way to look for Tate's tables of knots in either experimental or numerical data of quantum turbulence or any other turbulence where you can really track some quantity, some one-dimensional space curve in three-dimensional space very accurately. Okay, that's not what we'll do today. So what we use is another knot invariant, which was proposed again in the late 20s. And it's called the Alexander polynomial. And what it requires us to do is assign an orientation to a knot, which is not something that I've talked about in my definition, but it's easy enough to do. You just sort of move one way along a knot. And of course, if we're interested in quantized vortices, they already have some orientation to them. And then we simply define a crossing. And actually, I've denoted these two different crossings that are left-handed or right-handed, but it doesn't really matter. I simply move and stand on the over-crossing of the knot, look at the left, and assign that crossing this 1 minus t in the polynomial. We'll see how we construct it shortly. To the left of me, I give that loop a t, and to the right of it, I give it a minus 1. And this helps me construct my knot polynomial. Okay, so let's just do a very quick example with a trefoil knot. There's no orientation here, but I'll sketch it out in a second. This is colored, I think from where this is from, it was colored just to show that the trefoil knot is three-colorable, but it actually helps this example because we can assign each of the arcs a symbol, x0 to x2, and we can label each of the crossings A, B, and C. And so from this, we can apply Alexander's rules for constructing this polynomial. And we do this, let's just look at this first crossing. So the A crossing, and the orientation I'm going to pick is going to come this way here. So I'd stand on that loop, give myself a 1 minus t, look to the left, give myself the t, look to the right, and give it a minus 1, and the rest of the matrix I can just fill in like that. Alexander's rules in constructing this polynomial allows you to delete any row and any column, which simplifies things, at least for this example. Once you've got a very large number of crossings, it doesn't change things dramatically. But I choose to remove this row and this column. And then to compute the polynomial, I simply compute the matrix determinant. And that's how I compute this Alexander polynomial. And the crucial thing is, for what we're interested in here, is that this polynomial is invariant under these three Reidemeister moves. Just deleting it in terms of computing the matrix determinant. So you can show that the matrix determinant is the same if you remove the row and column up to some sort of factor of t. It can be any, I think, yeah. I think that's right. It may be that you have to remove a row and column that are actually adjacent to one another. I'd have to check, but I think for the example, there are a whole host of these knot polynomials that all have slightly different rules in how you construct them. But I think this one is actually any row and any column. Yes, yeah. So you just there's a factor t that you would. Yeah, exactly. Because this is invariant under these three Reidemeister moves, this thing is invariant under these shape-preserving homeomorphisms. So if I find, I'll show you an example. Will I show an example? But if I find a very, very complex knot that I could use these Reidemeister moves, this pushing and this poking and this twisting, anything apart from cutting the knot, and turn it back into an unknot, I'd find that this has a trivial matrix determinant once I work through it. So I could determine whether something that looks very complicated is actually just a simple unknot, just using this polynomial. So numerically, this is perfectly fine to write up and do. And unless you find something with a massive number of crossings where you've got to numerically work with a large matrix to compute its determinant, then it's perfectly fine. What this may point to, actually, is that we do encounter very complex knotted structures when we look at our three-dimensional simulations. So our procedure is simply to take a snapshot of a turbulent tangle that I'll show you shortly, break it up into a subset of loops, and for each of these loops, compute this Alexander polynomial. And what we'll do is, rather than trying to compare with Tate's tables for now, what we'll simply do is look at the degree of the polynomial and use that as some sort of measure of the complexity of the knot. Okay, and so it remains to look for Tate's knots in there, but as we'll see, we do find very complex knots, which may be beyond what you can find in Tate's tables anyway, just because the combinatorics of a knot with 87 crossings becomes pretty complex. Okay, this can all be, it's all pretty trivial to code up. And so a few examples, the trefoil knot we saw in the previous slide. An unknot just has a determinant of 1, and we find this very, very monstrous knot here, which has a degree of 82. As I say, the polynomial is quite complex, and it's not clear if there's a way to relate this back to Tate's tables anyway. So we can look at additional properties by looking at the crossing of different vortex loops, different space curves. We can look for things like the linking and the total linkage number. I won't focus too much on this. I'll just show one plot that shows that there are not just very complex knots in our tangle, but also a large number of links between these knots. And we can check more fundamental things like the energy, the total vortex line length, and the individual length of loops very, very easily. No. Next slide, I think. Yes. Okay, so the numerical approach that we're going to take, so I like this sort of analogy that Carlo drew in a paper a few years ago where you're sort of trying to see the wood for the trees. So the GP is argued to be this model of a single vortex. And I think now with sort of increasing computational power, this intersection between these two is more blurred, that you can perform large-scale numerical simulations with the GP and look at the dynamics of thousands of vortices. The point vortex model, which I'll use and I'll describe in the next slide, is meant to probe this mesoscale between the GP and then a more coarse-grained model, the Hall-Vinan equations, which really wouldn't be applicable here because we lose the notion of individual quantized vortices, which are crucial to computing these space curves to understand the topology of things. So it's this guy in the middle that we're going to plump for, and it's a very simple model to write a code for, and I think compared to the GP, the one advantage that it has here is that your simulations can be in an infinite volume. So you can just simulate an isolated tangle without having to worry about the boundaries. Because once vortices hit the boundaries and you don't have closed loops anymore, you'd probably have to invoke either tools of braid theory or do some more complicated algorithms to take into account something like periodic boundary conditions. And we won't have to do that with the vortex filament method, because as I say, we can work in an infinite volume. So how do we compute the motion of quantized vortices? Well, it's very straightforward. Our quantized vortices just define the superfluid vorticity field, and we simply uncurl that to get the velocity field, and then we can move our quantized vortices times according to this velocity field and repeat this procedure. And of course, numerically, we have to discretize our lines into a number of points, but all this is fairly straightforward. This integral is singular. Algorithms, or there's a precedent for how to desingularize this integral. And there is a drawback that reconnections are not part of this model, and we have to force them in this sort of hand-wavy manner by algorithmically cutting and pasting quantized vortex lines. But there's been a little bit of work to show that they're at least robust. Depending on the procedure, that you, sound like Britney Spears, that on the procedure that you take to do this chopping and pasting. Okay, so with these caveats in mind, we're going to move forward with this model. Another advantage compared to the GP, yeah. A reconnection will change the topology of an object. Yeah, the topology will change dynamically. Yeah. I'll show you. Yeah, so if you start with a knot, it will move and reconnect, and its topology will change just as in the GP simulations that I showed, or the experiments with water. So topological properties are affected by vortex reconnections. And this is the idea, to see if these reconnections mean that we just find loops or very simple knots because reconnections cause them to fall apart very quickly, even if they're formed by the nonlinear dynamics of the tangle. Another advantage compared to something like the GP is that there's a way to include finite temperature effects, And for the purposes here, we're really not interested in simulating a particular experiment, but using the normal fluid to drive the turbulence to create a steady state where we can probe statistics. Okay, and the way that we'll do that, I'm sure we're all familiar with this, but is to include mutual friction, so the scattering of thermal excitations from the vortex core, which comes from these two mutual friction coefficients, which couple the normal fluid to the superfluid component. So we'll ignore the superfluid component reacting or modifying the normal fluid component. This will simply be a drive which generates a steady state of quantum turbulence in the center of an infinite volume. Okay, so it's a sort of decades-old numerical strategy, and here's just an example of counterflow turbulence, so related by the sort of dawn of quantum turbulence from Joe Vinan. So here we just have a constant normal fluid flowing in this direction, and these quantized vortices are subject to this equation of motion. Vs total here is simply the Biot-Savart law for all intents and purposes here. And we can see that this generates a steady state, so initially there are a small number of vortex loops which grow rapidly due to the amplification of Kelvin waves via this Donnelly-Glaberson instability, which comes from the presence of the normal fluid, and then eventually dissipation of the superfluid component causes a steady state to be reached. Okay, and so our first results, I'm ready for a little bit of criticism here. We chose a normal fluid. What we wanted was a confined normal fluid so that we didn't have to deal with loops going to infinity or loops hitting boundaries or anything like that, because as I've argued, topological quantities will be more difficult to measure. And so what we chose was a summation of Fourier modes to mimic a multiscale flow, sort of appealing to window to things, which of course has the consequence that our velocity field is no longer incompressible, which is obviously a little bit fishy, but really our motivation was, as I say, just a way to generate quantum turbulence in an isolated region. And if you do that, you see an initial number of vortex rings that are quite smooth become perturbed, and you see this turbulent tangle develop. And what we can look at are various quantities. So what are plotted here are the vortex line length and the vortex energy, which we see effectively mirror each other. So there's a small number of vortex lines initially. They grow very rapidly due to the normal fluid driving them, and the energy does the same thing. And then we plot the total number of links, which I won't really discuss any further, but just to emphasize, there are a large number of links between these separate loops in our simulations. But the key thing is the Alexander polynomial. So what's plotted here is the largest degree of Alexander polynomial, the second largest degree, and the third largest degree. So what you see is these tangles are dominated by one or two very large, very complex knotted structures, and then below this a large number of more trivial structures and knots or trefoil knots or more simple topological objects. Okay, so we went back to the drawing board because obviously this normal fluid drive is very unphysical because of this compressibility of the normal fluid flow. And of course, one place you can look if you want to find chaotic confined flows are people interested in geomagnetism. So people are interested in how something like the Earth's magnetic field is generated, and what they use are toy models to probe dynamo theory. And of course, if you're interested in sort of the outer core of the Earth, then it's a confined object. You want something that's chaotic, perhaps time-dependent, or you're not going to generate a magnetic field. And the model that we look to is this Dudley-James model that was proposed at the end of the 80s, where you decompose your velocity field into a toroidal and poloidal component, because that ensures incompressibility of the flow. And the T2S2 flow is a very famous one that they analyzed analytically in their paper and showed that it generated a magnetic dynamo. And so we simply plumped with that, but added some time dependence. So these functions A and B are just sinusoidal functions just to give some time dependence to the flow. Okay, and so this is certainly an improvement because it maintains incompressibility, it's chaotic, time dependent, and so we use this to drive, again, a tangle of quantized vortices at the center of a of an infinite volume. And here we go. So I copied Davide with some cheesy music. But if it plays. Or if it's something more dramatic, though, you know. Jazz is true trivial for this. But essentially what you see is a bit of a mess of turbulent quantized vortices being driven by the normal fluid. You'll occasionally see colloidal structures appear. And occasionally small loops will pinch off. But once they move outside this region where the normal fluid is driving them, the temperature remains the same, but there's no normal fluid driving them anymore. So they very quickly shrink and are dissipated. We include all the loops in our analysis of the topology of the tangle, but these things don't fly off to infinity. They die very quickly once they move outside. And again, this box is just purely for visualization purposes. So if you see weird things like vortices leaving the box, it's just due to bad visualization, nothing else. We don't track the number. We don't track the individual number of. Well, maybe we do track the number of loops. The quantity that we use to sort of quantify the energy is simply the vortex line length. Is that kind of what you're interested in, or? The density increases. I'll show you on the next slide. So the density increases and then reaches a steady state, with fluctuations just due to the drive of the normal fluid. I don't know if this movie, I can't remember which of the drives it is. We perform the simulations with two different levels of drive, so simply a constant multiplied in front of the normal fluid. And that clearly affects the vortex line density that you reach here. I mean, because there's not a fixed volume, I guess you could do it within the sphere that contains the normal fluid. In fact, we just plotted the total vortex line length, which is a proxy for the vortex line density. But in both simulations, this grows quite rapidly and then saturates at some steady state as dissipation matches the drive. Well, with the GP, it's not clear how you could drive it anyway to reach some steady state, unless you considered, say, a large volume and you injected, you multiplied the wave function every now and again by a vortex ring at the center to sort of mimic the injection of vortex rings and generated a steady state tangle that way. But again, you probably have the volume of the problem of rings leaving that central region, interacting with the boundaries, and then sort of making quantifying topology just a little bit more difficult. I don't think it's undoable, but certainly this approach makes things a bit simpler that way. No, sorry if I've not been clear. This is all within a superfluid. This drive was just motivated. It came from MHD because it's a suitable model for geophysical turbulence, or a very simplified model for geophysical turbulence. And so what we see are different drives. If you can see, there is a difference in vortex line density. Again, where this loop sort of leaves this volume is again just a visualization issue. Oops, scoot ahead. And again, what we can plot as a function of time is the largest Alexander polynomial, the degree of the largest degree of the Alexander. We see that this is dependent on the drive, as one might expect. So as the tangle density increases, it becomes more complex. Once we can quantify this Alexander polynomial. So these is the probability of a knot. So I'm not an experimentalist, but I've even brought a demonstration that I just picked these out of my bag, right? And I'm sure we're all familiar that anything like headphones or any long cable, the probability of finding some sort of complex topology is almost 1. Okay, but what about our quantized vortices? Well, with this Alexander polynomial, it's really straightforward. If we find an Alexander polynomial whose determinant is 1, we know that that's just the unknot. And what we find if you you remember, we can easily compute the length of individual vortex loops within our simulation. And this is all done within this steady state regime once the transient has passed and our vortex line density is saturated at some mean value. And we find this sigmoidal shape where the probability is dependent on the vortex line density, as you might expect. And the motivation for fitting this sigmoidal shape is really motivated by Nobel Prize winning research, not quite the real Nobel, but the Ig Nobel, and this nice experiment that was done 10 years ago. I think that should be 2000. That should either be 2017 or that should be 2008. I don't think it was delayed for that long. Where they, let's see if I can play this. They have a length of rope in a box that they spin. And this is spun for a certain period of time. And then they simply connect the ends up in, I don't know if they just go in and connect them, or if there's some more sort of algorithmic approach to how they connect it up. But again, you find a very similar sort of shape. So I'm not saying that we can treat just quantized vortices as random lines being tumbled, but we see this, the fitting parameters are almost the same. We see a difference in the sort of total probability, and in their paper they ascribe that to the stiffness of the rope that they use. And I think they actually tried experiments with different stiffnesses and found that the probability that this curve saturates to is dependent on the stiffness of the rope, which intuitively makes sense. Now, a rope is maybe not being tumbled is a sort of neat example, but maybe not quite as deep as looking at something like DNA. So these are very early simulations, Monte Carlo simulations of DNA molecules in a confined volume. And what they find is a similar sort of thing, that very rapidly, depending on the length of the simulated DNA strand, the probability of finding a knot rapidly increases. These different curves are just for different confining volumes. And so sort of intuitively makes sense if you confine the DNA stronger and stronger. So R, I think, is just the radius of the confining volume. If you pack them in more densely, then this curve grows more rapidly. And later studies, but I've not included them, show the same sort of saturation that we see here, showing that there is some connection, at least, between the knotted dynamics of quantized vortices and Monte Carlo simulations of DNA molecules, and that we find a probability dependent on the length of the chain. Yeah. It's a histogram, so these are binned. So within each of these bins, they're, depending on how long the length of the loop is. So there are clearly less knots up here, and this might be tens of thousands of knots which contribute to this probability within this bin of the histogram. Up here, it's far fewer, but we always have about 10 knots within these bins. Apart from if the probability is 0, then it's classified as being an unknot. Yeah. So all knots are on that diagram. So we're ignoring the kind of complexity knot and just making the distinction between are you knotted or not. Here's sort of moving towards the kind of complexity of the knot. So we can distinguish the different loop lengths, as I've said, and then we can simply plot this scatter plot of the degree of the Alexander polynomial against the length of the loop. And again, we find what we might expect. There's this relationship. As the loop gets longer, it's more likely to be in a more complex knot. Which again, naively is probably what you might expect. But the final thing that we propose is not something that I could find in the literature for DNA or other molecules that people look at their sort of knotted or topological properties, but is what we call a knot spectrum. It's not a spectrum, it's a distribution. But it's sort of, we hoped it was analogous to other spectra in fluid dynamics. And what we look at is effectively the frequency or the probability mass function of finding a particular knot of a different degree in both our simulations. And we see these curves overlap quite strongly. The higher drive, we obviously have larger knots because we see larger vortex loop lengths. But at least for both of these simulations, and it's not a huge sample, we find this scaling, which which fits fairly well, of minus 1.5, which we don't with theory finish yet. But as I say, it'd be interesting to see, to dig more deeply into the literature or perform these Monte Carlo simulations ourselves of DNA and see if this is something that's universal or is dependent on the way that we drive the quantum turbulence. That's where just to show that sort of humans have about 100 kilometers is a gospel on a tidal island called Lindisfarne. And there's this famous gospels which date to sort of 800 AD, something like that. And they're beautifully illustrated, and they clearly have this sort of Celtic origin as well. So this is one of the folio pages from the Gospel of Matthew, something like that. And you see these beautiful Celtic knots embedded here to show that humans have had a long interest in knots, and if you go back and find any artwork from, well, not any artwork, but plenty of artwork contains these complex topological structures because they're neat and they're interesting. Okay, I'll leave you to read my outlook because I'm running out of time. So, thanks.